Good day, I'm Norman Wildberger. We are currently gathering some experience and familiarity with some basic ideas in elementary algebra, on our way to establishing proper foundations for the subject. So at this point we are still talking relatively loosely and informally about the subject. Today I'm going to talk about the binomial theorem, which is of course a major subject for high school mathematics and an important and practical tool for algebra. It starts out by expanding a term like a plus b squared. We've seen that that's a squared plus 2ab plus b squared. If you now expand a plus b cubed, for example, if you take this and you multiply it by a plus b, then you get a cubed plus 3a squared b plus 3ab squared plus b cubed. And here is a plus b to the fourth with coefficients 1, 4, 6, 4, 1. The terms all have a's and b's in them, with the power of a's decreasing as we move along and the powers of b increasing as we move along. And there's a kind of a symmetry, as you'd expect, between the a's and the b's. And here's a plus b to the fifth with coefficients 1, 5, 10, 10, 5, 1. And if you stare at this for a little while, you see that there's a pattern, and there are some pleasant relationships between the various coefficients from one line to another. And this is usually encoded in a very familiar kind of table called Pascal's triangle, which all high school students meet. And here it is right here, where we've essentially taken the coefficients of the various lines here and written them out in rows. The binomial theorem is sometimes presented as something of a mysterious thing, but it really is a very systematic consequence of the distributive law. Here is the distributive law applied to a plus b times x plus y. We expect that there's going to be four terms: a times x plus a times y plus b times x plus b times y. So there are the four terms. Now if we look at this general formula in the special case when the x and y are the same as a and b, then if we just copy this over, we would get a times a plus a times b plus b times a plus b times b. So in reality there are four terms that you get when you expand out a plus b squared using the distributive law. It's just that the ab and the ba term happen to be the same because a and b commute, they're numbers after all. And so they coalesce to give us 2ab. Let's have a look to see what happens if we multiply three terms, each with two components. A plus b times x plus y times c plus d. Now there are 8 possible terms that result. And now when we look at this general case, in the special case when all the terms are a plus b, then the 8 terms look like this: AAA plus AAB plus ABA and so on, where I've recorded the order of the terms in the way they appear. And now we see that the reason why there's 3a squared b occurring in the result is because there are 3 terms here that have 2 a's and 1 b in them, namely this one, and this one. So these 3 terms combine to give us 3a squared b. So amongst the original 8 terms, some of them are coalescing because they have the same numbers of a's and b's in them. It's telling us that the coefficients in the binomial theorem are actually counting something. They're counting the number of ways of writing down a little triple like this, using a certain number of a's and a certain number of b's. To clarify that idea, let's have a look at a plus b to the fourth. Here's a plus b 4 times. When we multiply these terms out, there's going to be 16 terms that appear altogether, because we have 2 times 2 times 2 times 2 choices. So we're going to end up with a sum of terms of the form x, y, z, w, where each of the x, y, z, and w can be either a or b. And now there's a nice geometrical way of interpreting these strings of A's and B's in terms of paths on a diagram, a two-dimensional diagram. So we agree that the letter A represents a step downwards, and the letter B represents a step to the right. And we're starting up here in this little grid. So the word AABA, that particular string of letters, represents a path. A path obtained by doing an A step, then another A step, then a B step, and then another A step. So this is a path from this point here, which we might call 0, 0, to this point here, which we might call 3, 1. Notice that this indexing has this coordinate as the first entry and this coordinate as the second. Now, there are 16 such paths of length 4 altogether, and each of these corresponds to a term in this sum. So in other words, the expansion here is just corresponding to various paths of length 4 that we can go on in this little grid if we're always either going down or to the right. And we're allowed to take any 4 steps we want. So for example, A plus B to the 4th, which we've seen is this expression here. This coefficient of 4 represents the 4 possible ways of getting from here to here. And what are those 4 possible ways? Well, there's AAAB, or AABA, or ABAA, or BAAA. Those are the 4 different words in the A's and B's that have 3 A's altogether and 1 B. So we can record this combinatorial information, because this is really part of combinatorics, the art of counting, by writing down the number of paths on the actual vertex that we're counting from the origin. So there are 4 paths from here to here, so we could write a 4 right there. There are 6 paths from here to here right at this point, we could put a 6 right there. And so we could encode the binomial theorem in a table where the grid is oriented like this. And what we get when we do that is something both interesting and familiar. The table that we get is one that we are very familiar with. We could call it Pascal's array now, because it's much like Pascal's triangle, except it's a little bit oriented with the corner up here instead. And what we recognize is that it's in fact exactly the same as the difference table for triangular numbers that we've written down a number of times already. So this row right here, 1, 3, 6, 10, 15, 21, 28, that's the sequence of triangular numbers. And this is just the difference table for that sequence. So along the diagonals like this, we have the various coefficients of A plus B to the n. In this case, n equals 4. 1, 4, 6, 4, 1. And this entry 10 is counting the number of paths from the corner to the position where we're always either going down or to the right. So this gives us now a new interpretation of what we used to be thinking about as triangular numbers, tetrahedral numbers, higher dimensional triangular or tetrahedral numbers. Here now is another way of thinking about this array, as it's counting some combinatorial object, namely numbers of paths. And this description of this array has some immediate advantages. First of all, it makes the symmetry between the rows and the columns obvious. The number of paths from here to here is obviously going to be the same as the number of paths from here to here. Our previous analysis did not reveal that, in fact, the triangular numbers were not just appearing here, but were also appearing down this column. Next time, we're going to look at the actual nature of the entries of this important table. These are numbers which actually have formulas associated to them, which is one of the points of algebra. These formulas are called binomial coefficients, and they're quite interesting numbers. We're going to have a look at that. I hope you're going to join me for that. I'm Norman Wildberger. Thanks for listening.